This is a video about section 2.4 about primality testing in Stein's elementary number theory book. The first theorem we run into is this concept about pseudoprimality. And what it is, it's kind of a test to see if a given integer is a prime number. So an integer p that's bigger than 1 is prime if and only if for every non-zero a mod p, so like for every non-zero equivalence class mod p, if you want to think of it that way, a raised to the p minus first power has to be equivalent to 1 mod p. So what's the proof of this look like? Well, if p is a prime number, then, so in other words, I'm kind of proving p implies q, so assume p is prime. We want to prove that this happens. But if I focus, what is this then? If p is prime, then this exponent p minus 1, that's 5p. And I know Euler's theorem, which is referenced right here, Euler's theorem told me that a raised to the 5p power is always going to be equivalent to 1 mod p. So that is why the forward direction of this theorem holds. Now for the other direction, what we're actually going to do, we want to prove p implies q. In other words, if this holds, then p is prime. What we're actually going to do is do the contrapositive. Let's suppose p is not prime. And so if I do that then, if p is not prime, then p is composite, and that means that p has some divisor. And so p should have a divisor, we'll call it a, and a should be between 2 and p, or it's strictly less than p, and it's bigger than or equal to 2. So I want something that's not equal to p itself. Now let's think about what would happen if a to the p minus 1 was congruent to 1 mod p. Well, think about, how do you do modular arithmetic? That says that p should divide the difference of a to the p minus 1 and 1. And so that's what we're saying right here. That's just, again, definition of modular arithmetic here. What else did I assume, though? I have assumed that a is a divisor of p, which means that a divides p. And now if you think about, well, if p divides that, a to the p minus 1, and a divides p, well, then a should divide this as well. So in other words, if you could rewrite p as a times k, then this statement says that a also divides a to the p minus 1 minus 1. And so we are, if you've been following that part, we're right here. So a divides that difference. And now again, let's write down the definition of divisibility here. So what we could say is, say a times k. I maybe used my k a little bit prematurely a second ago. So here's what I'm going to use. A times k is equal to a to the p minus 1 minus 1. A times something should give me that number that it divides. So now what we're going to do is rearrange it. So we're going to rearrange it a little bit to try to get 1 by itself. And if you rearrange this to get 1 by itself, you should end up with something like this. A to the p minus 1 minus a times k equals 1. Notice you could factor an a off the left side, and that leaves you with a times a to the p minus 2 minus k is equal to 1. Now think about what that says. That says that a times something gives you 1, which of course means that a divides 1. But that's ridiculous since a was chosen to be between 2 and p. So that's our contradiction. So what did we just contradict? Really right here, we're sort of saying, suppose by way of contradiction that this did happen, that it was congruent, a to the p minus 1 is congruent to 1 mod p. We just showed that you get something false. Therefore, this can't happen. So what did we just prove again? We proved that when p is composite, then this formula does not hold. So we just proved not p implies not q, therefore that's equivalent to q implies p. Okay, so we finished this if and only if here. And why is this called maybe pseudoprimality? So to check if an integer is prime, that involves us computing perhaps a whole lot of these doing a whole lot of these computations here, which is perhaps infeasible, in the very least inefficient. And so what we'd see though is that if I got a to the p minus 1 is congruent to 1 mod p for a whole lot of these bases a, then it seems pretty likely that that number p is actually prime. And that's why we're going to say pseudo-prime here, right? It's kind of like almost by proof by example. If I see it holds a lot of times, I bet you it's true, but it's not really proof that it's true. So this is like one of those kinds of things where, here's kind of the theory of what it says, but to use this in practice, it's kind of hard to do. On the other hand, what is nice about it, well, this says as soon as you find one base A where this equivalence fails, then P is not prime. So in fact, really what maybe the upshot of this theorem is it's easy to check and see if something's composite. And so for example, and then by the way, down here, on the other hand, maybe I kind of got ahead of myself a little bit there. So this paragraph just kind of talks through what I was just saying as well. So we're either quickly going to prove that n's composite, or we're just going to try to convince ourselves that n is pretty likely prime. But of course, it's not really definitive, right, if I was doing this by hand. So to give you an example, if you were able to show that, say, 2 raised to the n minus first power was not equivalent to 1 mod n, right, you found a base 2 where this equivalence does not hold, then you can just say that n is not prime, and that's fast. But then on the other hand, right, if a to the n minus 1 is congruent to 1 mod p for, a few or a bunch of these a's, it seems pretty likely that n is prime, but you've got to check all the a's that are less than p, so or less than n. So if n's like a really large number, that's a lot of computations to do. So anyway, for this reason that it's pretty likely that it's prime, that's why we're going to call such a number n a pseudoprime. And that leads us to a pretty famous type of number. It's a type of composite number, n, and they're going to be called Carmichael numbers. So they're pretty famous. So far, we've had some different types of numbers that we've named. Maybe you remember the Mersenne primes, were primes that have the form 2 to the p minus 1, where p is a prime. Remember that I'm not saying that this expression is always prime, just when for the primes p, where this expression's prime, we call this a Mersenne prime. And it's a fun or open and exciting problem, I guess, to keep trying to compute the next biggest Mersenne prime. You can check those out. So I've got kind of this other type of number I'm going to name, and these are like very special composite numbers, and they're called Carmichael numbers. And what's the property? Well, it's the property that's, I get this equivalence, a to the n minus 1 is congruent to 1 mod n, anytime your base is relatively prime to n. So like these Carmichael numbers, they kind of want to act like, it's almost like they want to act like primes according to the pseudoprimality test. And let's see, there's some pretty deep mathematics that goes on, but the first Carmichael number we run into is 561, and as it says here, there's a theorem that says that there are infinitely many Carmichael numbers. But again, that's some pretty deep stuff. You can see the reference at the end of Stein's book if you want to go dig around for that research paper. But to show you an example of maybe how we might use the pseudoprimality test, what if I wanted to know is p times 323 prime? Well, if I want to know if that's prime, think about what this says. I've got to check every single base a, so starting with 2 and working my way up to 322, I guess, is such a base to the 323 minus 1 power equivalent to 1 on 323. So we'll start with 2. Let's start with that base. That seems like a natural place to start. Let's compute. What is 2 to the, notice 322 is p minus 1. What is that mod 223? And this is where the previous video about computing huge powers, remember what we're going to try to do is find the binary representation of 322. And I'm only going to keep the powers where I had a coefficient of 1 in that binary representation. So really all I'm looking at here is where are, again, watch the previous video, where are these epsilon i's 1? So it's these factors here. So in order to compute 2 to the 322 power, really what I need to do is just multiply 4 times 188 times 35. And that's what we're going to do here. And then we reduce that 300 by mod 323, and you should get 157. Well, now wait a minute. This was supposed to, if this was prime, this needed to be equal to or congruent to 1 mod 323. 157 is not 1. Therefore, we've just shown fairly quickly that this number, 2 to the 322, is not a prime number. And in fact, it factors. Although, like what just happened, I was able to show you that, yeah, that thing's not prime. As far as the pseudoprimality test goes, it didn't give me any information as to how 323 factors, right? It just tells you that, yes, it does factor. It's one of those fun things in math. Kind of like a convergence test. I can tell you it converges, but all the convergence tests in Calc 2, I have no idea what it converges to. You need some more hardcore math to do that. Let's see. And in the last part here, we can try to, and just to show too, some more about factoring here. So what if I took, for example, what if I took some massive number? I have no idea how to say that in people words. But what we could show is 2 to the 1 less than this number, in other words, change this 3 to a 2, is not congruent to 1 mod n, so that would show that this number is composite. So again, where does this 2 come from? Why is it special? Well, because I've got to check every single base less than or equal to that gigantic n, and so 2 would be the first maybe non-trivial, non-zero one. What do I mean by non-trivial? I guess, if a is 1 here, then of course this is satisfied. That's why I mean 2 is the first kind of interesting base. So that's why in both of these examples you're starting with 2. But if you sub this into Sage and you ask Sage to do, okay, go ahead, do mod 2. So I'm going to take the element 2 in the ring Z mod nz, where, oh, good lord, that's my n, and I'm going to raise it to the n minus first power. And remember, if I was to get the impression that this was prime, I would expect this to be 1. And remember, that doesn't tell me that it's prime. That just tells me keep going, go to the next base 3. But right away, I see that I don't get a 1. That tells me to stop this process. And so that tells me that this thing is composite. Now, again, it's composite, cool. So this number is composite. None of this tells me about what the factors are. And you could try to factor in Sage. Sage has this built-in thing called factor n. And if you try to run it, the author did, and he comments here that expect it to take a little bit, because in general, it's kind of hard to factor some of these really, really big numbers. And what you get, though, is you do get that it factors into these 2 primes right here. And maybe you're thinking at this point, okay, factoring. I know how to factor. It's not a difficult concept, but what's kind of mind-blowing again is even factoring these big numbers with computers is a very hard problem. And this is kind of setting the stage for some of the cryptography stuff we're going to do later on.